Onur Mutlu, Computer Architecture Introduction, Part 2. This episode is discussing the fundamental takeaways of Onur's lecture. The reason we're doing the lecture is because, like we always do, we discuss things we're reading, things we're working on today. The purpose of this podcast is to give people a sense for what it feels like to run a hedge fund. And partly the way we run this hedge fund is by educating ourselves, going back to academics every now and then, tip our toes in the water. And this is exactly what we're doing. We've done this course a couple of years ago. We're doing it again. Computer architecture is a fast-moving field, particularly now. And Onur is one of the most inspirational professors out there. So together, this makes for a really good example of why we believe it's important to go back, read, educate yourself, and also to get inspired by people like Onur. So the second part of this intro in his lecture is the takeaway is really the fundamental concepts of computer architecture, which are, in Onur's words, look back, look forward, look up, and look down. I'm going to discuss what that exactly means. Computer architecture is, of course, the discipline of designing computers optimally for now and the future, but I think it also applies to the rest of the world. But let's say, how do you design a hedge fund? You have design constraints. You have to make sure you follow certain principles. So all of these things that we do at Orange Capital Partners, Onur applies them also to the computer architecture discipline. So this is a very, very interesting episode. I highly recommend it. And I don't think I have to mention this again, but Onur is by far the most inspirational computer science professor and one of the most inspirational talkers that we actually came across in the last couple of years. This is not even on podcast. It's May 3rd, 2022. This is Crimdelco. Since the last update, we're up 3%. The market's up 70 basis points. For the year, we're down 23.7%. The market is down, 23.6%. The market is down 12.7%. We're underperforming by 10.9%. Onur Mutlu, Computer Architecture Introduction, Part 2. In this Part 2, Onur continues with his elaboration of what is computer architecture and why it's important. The reason it's important is because you need to be able to understand what are the needs of the current computer community, and then also hopefully you can design computers so they can serve for workloads in the future. Partly those are workloads that we know today. So for example, genomics is a workload that is already known today and thus doesn't have good solutions. And then there is things like in the future, in the sense that, let's say, we don't even know what could be a workload in the future, and we want to understand what kind of design we can employ today to be flexible enough for the future. So let's start with Calatrava. Calatrava is an architect who has built a couple of things in Switzerland, for example, where Onur is currently a professor at the Polytech in Zurich. And Calatrava's fundamental principle of architecture is two principles. One is use materials optimally, and number two is take advantage of the ability of organisms to move, shape themselves, and grow. And those are the two things that I think Onur is taking at heart, because he wants his computers to be, of course, optimally designed for the current workloads, but also he wants them to be able to move. In other words, he wants them to be able to evolve with the needs of workloads. Now, one great example of what workload need means is, for example, the fact that we had workloads in the past were, let's say, driven by the internet, things like transactions, Amazon. And the workloads of the future, or actually the present and the near future, are workloads driven by machine learning. In other words, driven by data. Machine learning is the ability to design a computer and program a computer in a way that it does things without explicit programming. That's what machine learning actually means. In other words, the computer is trained by data and then reads new data and acts accordingly. And the way this happens is through algorithms such as principal component analysis, which is a subroutine, linear equations, least square methods. All those things are subroutines, linear algebra subroutines, which are used in algorithms that are modern machine learning is based upon. A subroutine is, let's call it sort of within the machine learning stack. We have the algorithm, which is based on linear algebra. Most of machine learning happens through linear algebra, because linear algebra totally answers the question, how do variables relate to each other. And more concretely, you have a matrix X times a vector X equals vector B. Matrix X is known, matrix A is known, and vector B is known. And you want to understand vector X, which is, let's say, in the parlance of machine learning, is the weights. And those weights can be figured out by inverting the matrix A, and that's something that we can do with classical computers, but we could also do with quantum computers much faster. A matrix A, so vector X equals matrix A inverted times vector B, which is the actual result that you're observing. So that's just one example of a subroutine which is necessary to do modern machine learning. And I think I want to use this example because it's a beautiful example to illustrate what Onur Mutlu means when he talks about look back, forward, up, and down. This is a quote from somebody, and I think it was Frank Lloyd Wright. I'm not sure. There's a couple of quotes in the lecture from Frank Lloyd Wright, from Calatrava, and then from Hemmings, which is a computer architect. And this is not that important who said what. Let's just stick with the concept. So looking up and down is exactly a nice example of what's happening right now. We've spoken about this already in one of the previous episodes. When we look up, we think of the nature of the problems. The nature of the problems, let's say we have a fundamental problem, which is linear algebra. We want to be faster at doing linear algebra subroutines so we can analyze a lot more data. When we look forward, we dream about, let's say, self-driving cars, we dream about genomics, we dream about personalized medicine. When we look backwards, we look at, okay, what has been done in the past. We have accelerators, NVIDIA, AMD, and then we have all the TPUs by Google. We have the stuff that Tesla's doing. We have chip startups such as Graphcore and Cerberus and many others. So this is what's going on in the near past, and also in the further back, we had general purpose computing, CPU, and all that stuff. And now if we look down, and this is predict the future of technology, this is the key. I think this is where Orange Capital Partners is putting a particular amount of resources, because we believe that if we can predict the future of technology, we can predict the future workloads, and we can predict future businesses. And since compute is highly correlated with wealth generation, we believe that we can actually succeed in our mission, which is generate wealth by investing in fundamentally new concepts and engineering practices. In other words, the fundamentally new concepts and engineering practices that we focused on are those which are driven by new innovations in compute, and compute is driven by technology. And very concretely, this means, for example, right now we're looking at quantum computing. Quantum computing is actually, according to Seth Lloyd and many others, and a few papers that we're reading, and the course that we're doing right now at Toronto, is able to probably in the next 1 or 2 years really do huge advances in BLAST, which is the basic linear algebra subroutines. So if we can get that, then we can actually do, for example, comparisons, which is one of the big problems that genomics is built on today. So genomics is a very broad field, but one of the major problems genomics has is simply compare stuff. You read the genome, 3 billion base pairs, and you want to know if the next genome that you read is similar to the genome that you just read. You need to compare 3 billion base pairs. And there are algorithms to do that, and we can do it with today's compute architecture and compute power and all that stuff, and all the constraints that we have on today's computing infrastructure. We can do it, but within the concept of quantum mechanics and using quantum computers that are built on quantum mechanics, we could do comparisons in orders and orders, many orders, 3, 4, 5, 6, 7 orders of magnitude faster with less energy consumption than today. And that means that we could do a lot more data comparison. We could do also comparison, not just of comparing one genome with the other, but also relationships between base pairs, relationships between genomes with other genomes, so metagenomes, all that stuff. We could do a lot more comparisons, a lot more interactions if we had functioning quantum computers, and we're not very far away from being able to do those kinds of things. So that enables new workloads in the genomic space, which enables solving new problems, which enables new businesses. So this is a great example of how Onur Mutlu's course is really transcending away from just computer architecture, which in itself is an important subject, towards the application of anything you do in life, in particular that's in the hedge fund business. The purpose of this podcast is to give people a sense of what it feels like to run a hedge fund. So what we want to do now is really translate what Onur said for computer architecture to the hedge fund business. Look backwards, look forward, look down, look up, look everywhere. And then design your hedge fund in a way that it's optimal to your design constraint. Our design constraint is our purpose is to generate wealth. This is the design constraint number one. And the only real constraint we have is we need to be able to survive. So that means we don't care about things like volatility. We don't care about things like looking good in front of fund of funds. None of that stuff. We don't care about having a career. We don't care about being on Bloomberg. We don't care about competing with Bill Ackman or none of that stuff. But we need to be able to survive. That means our cost structure has to be in check so that we can survive very, very high drawdowns, which of course is part of the business. The main design constraint is generate wealth. We decided that generation of wealth is driven by compute, so we focus on compute, we focus on looking down, predicting the future of technology. In this case, we're looking at new applications in traditional computer science, or classical, computer science. So we look at things that Onur is talking about, such as optimizing for memory, bandwidth. So the main constraint in classical compute is to be able to move memory back and forth from the CPU, and the solutions are in-memory compute or Cerberus, which is very high, large, putting compute and memory together on a very large wafer. Then another constraint is power, energy. So those are the two main, power and energy. Of course, also scalability and security are part of it. But the main concerns that Onur is talking about is really power and memory, which is related, of course, because moving memory back and forth from memory to the CPU is the main consumption of power. So these are the classical constraints that we're looking at, and we're looking at companies that solve them so they can do faster compute. And then we're looking at quantum solutions, such as, like I mentioned in the prelude, and also before I just said this, I spoke about the fact that it looks like quantum computers are ready soon to solve subroutines such as principal component analysis and just playing comparisons and all that stuff, because of the parallelism within quantum computing. And if we have that, we can then solve new types of workloads. So we spend a lot of time looking down at Orange Capital Partners, which is try to predict the future of technology. We also look forward. We listen to the dreamers. We listen to what's possible with blockchain, what's possible with self-driving, what's possible with quantum computing, what's possible with genomics, personalized medicine. We listen to these things, but we always also look down. Okay, what is the technology today? Where is it going to go forward? We look up in terms of what is nature and what the organic structure of nature. So things like again, like we have medicine, personalized medicine, which is certainly a problem that for sure will have demand. And then we also look back. We look in terms of, okay, what has been done more recently and what can be done right now and what can be done in the near future. So Onur's concept of looking in all directions when it comes to computer architecture is very, very well suited also for the hedge fund industry. Another concept that he talks about is principles. He talks about the Calatrava principle, the Frank Lloyd Wright principle. Frank Lloyd Wright, whose principle is basically to focus on principle and not on precedent. This is exactly what we do in Orange Capital Partners. Our whole investment thesis is based on 4 principles, based on the 4 books, Peter Thiel 021, Clayton Christensen, The Innovator's Dilemma, Jim McKelvey, The Innovation Stack, and David Deutsch, The Beginning of Infinity. Those are the 4 books that we draw our principles from. Doesn't mean other books are not as good, but this is the focus that we have. And we believe that principles are more suited than, let's say, rules or algorithms or things like that, just because principles are a little bit more flexible. They apply to the Calatrava principle of pun intended here, of using the adaptability, the ability to grow, the ability to move. All these things, principles have that flexibility, and our fund needs to be flexible enough to move with the times, to move with the technology and the problems and the questions that are being asked. Finally, maybe I just want to get back to one of the key questions of why we're so focused on compute. Why aren't we focused on things like, I don't know, design or management skills or whatever else people use to evaluate businesses? And of course, all these things matter, but compute is the key, because compute is really just another word for iteration, and iteration is the key for disruption. So we've spoken about this many times. Iteration is the key for disruption, And the iteration, the faster you can iterate with a lower cost of error correction, the faster you can disrupt businesses. So businesses are driven by iteration. Innovation stocks are built through iteration. And the key of iteration is to find ways to iterate at faster, lower cost. And compute is just one way. It's a very suitable way to do that because compute allows you to iterate much faster and much lower cost. Mathematics is basically a shortcut within the iteration sphere, if you want. So mathematics helps you to iterate faster and even let's say circumvent some of the constraints that you have in the physical space. And compute is allowing you to iterate fast. And the speed of iteration and the cost of error correction are key. We introduced this in our natural Sharpe ratio concept, where we spoke about a company that can have a lot of projects, iterate faster, and the lower cost of error correction will eventually generate more wealth. This is fundamentally how we see the world. This is why this course of Onur Mutlu is so key to us. It's one, because it is about compute, and two, it also has this transcendent quality of teaching us what design is about, what architecture is about, how we should even think about designing systems. And of course, our hedge fund, Orange Capital Partners, is a system too. It's not a chip, but it's a system, and it has the same vectors that we need to think about. Let's say constraint. What's the design constraint? What's the goal? What's the purpose? All of these things matter as much to us as they matter to a computer architect. So to summarize, Onur Mutlu's course, Computer Architecture, is important to us for two reasons. One is it gives us a sense for where computer architecture is today and where it's heading. And second, it also helps us transcend into our own problem set as a hedge fund. What are we optimizing for? How are we designing ourselves? How are we organizing ourselves? What is our design constraint? So these are very, very valid questions that we ask ourselves, not all the time, hopefully, because we hope that some of it is, let's say, that stands the proof of time. But we are also flexible. We use Calatrava's concept of the organisms that are able to grow, move, and change their shape. So we want to be like that. But we also need to be, of course, stable and secure. And Calatrava's bridges and railway stations exactly follow that principle. Finally, of course, the key concept that we at Orange Capital Partners spend most resources on is to look down, which is predict the future of technology, particularly predict the future of compute, because we believe compute is at the heart of all the other technologies, for example, material science, battery technology, self-driving cars, all of the things that drive genomics, personalized medicine, all of these things that drive our portfolio companies are fundamentally driven by compute. So we look at compute and the future of compute. Where are we today and where are we going? And one of the key concepts there, of course, is quantum computing. And we believe in the next 2 to 5 years will actually fundamentally change the way compute is done and enable massively new wealth generation opportunities. Thank you.